Okay, hello and welcome to part one. Everything you need to know to derive the equation of the ellipse. In this video, I'm going to show you how to derive the equation for an ellipse. And I'm going to tell you just about everything you need to know for an ellipse. So let's get started. First, let's look at an ellipse and see what it is we need to know. Okay, here's an ellipse I created. And first, what I did was I made this foci. I have foci P and foci A. An ellipse has two foci. And at this first foci, I put a green dot, and I'm calling that Earth. But it could be anything. This could be the sun with the Earth traveling around the sun. But this foci P, I called it P because the closest point along the ellipse as the object travels along the ellipse, the closest point to this foci is called perigee for Earth. And the furthest point from this foci P is called apogee. So the closest point to this foci is called foci A. And as you can see, as a satellite rotates around Earth, it travels an elliptical path. Now, this could be the sun, and this object could be Earth orbiting the sun. Okay, this point here, rather than a satellite, I call that D. And from foci A to D, I call D1. From foci P to D, I call D2. Okay, and let me see, in the middle, from the center of the ellipse to foci A, I call C. And from the center of the ellipse to foci P is C. That's the same distance. Okay, let's run this program and see how this orbit takes place. As you can see, the way I have this configured, this satellite is orbiting Earth and it rotates around. Now, you'll notice there's something very special. Let me pause this for a moment. There's something very special about D1 and D2. As you notice, as D rotates along this ellipse, about this ellipse, D1 and D2 length remains the same. And as you can see, the length D1 and D2 is equal to the length of the ellipse, the total length of the ellipse, which is 2a. So from the center of the ellipse to apogee, and from the center of the ellipse to perigee is the distance of 2a. Therefore, D1 and D2 is equal to 2a. And we're going to solve that equation. We're going to solve for D1 and D2 when we get back to our presentation. Okay, let's get started. Okay, let me arrange this where we can see it. Okay, so let's talk about this ellipse. Well, at the foci P, we have Earth, and at point D, we have some satellite that's orbiting Earth. We call this distance from foci P to D, we call that D2. And from foci A to D, we call that D1. Now, the distance from the center of the ellipse to foci A is called minus c, and the distance from the center of the ellipse to foci P we call distance c. Okay, so that's minus c0 to the left and plus c0 to the right. When we locate D, we call this x and y. So that's located at some x and some y. So from the center of the ellipse to the top of the ellipse, that's the semi-minor axis B. And from the center of the ellipse to perigee, and from the center of the ellipse to apogee, that's called the semi-major axis A, both sides, semi-major axis A. Okay, so let's get started. Let's calculate the length of these lines, D1 and D2, using the distance formula we learned in algebra. Okay, let's get started. D1 and D2 is located at, D1 is located at XY, comma, minus C, comma, 0. And D2 is located at some XY, C, 0. That's the location of D1 and D2. Our points are located at foci A, minus C, 0, foci P, C, 0, and point D is X and Y. The distance formula is D is equal to the square root of the quantity x2 minus x1 squared plus y2 minus y1 squared. That's our distance formula. Okay. Which one do we call 1 and 2? Well, we can call x, y1 minus c0, 2, or we can call xy2 and minus c0, 1. I just picked xy as 1 and minus c0 as 2. Either one will work fine. So D1 is equal to, this is the point's location, x1, y1, x2, y2. The first one is x1, y1. The second is x2, y2. So from the Pythagorean theorem, what is x2? Well, here's 2. x2 is what? Minus c. What is x1? x1 is what? X. What is y2? y2 is what? 0. And y1 is what? y1 is y. Okay? That's why I labeled them groups 1 and 2, so we can know which is which. And we do the same thing with D2. Okay. What is x2? x2 is, this is number 2. x2 is what? C. And x1 is what? X. y2 is, this 2 is what? 0. And y1 is what? Y. So therefore, D1 and D2 is equal to the following. In an ellipse, D1 plus D2 is equal to 2A. You remember that? D1 plus D2 is equal to 2A, the total length of the ellipse. From apogee to perigee is 2A. Therefore, we plug in D1 and D2, D1 and D2. So D1 plus D2 is equal to 2A. Now we move one square root to the right side. pick which one you want to move. I picked the minus square with the minus c in it. And I moved that to the right side. So that leaves one square root on one side. And on the other side, it leaves 2a minus the square root of that quantity. Let's continue. Okay, here's our previous equation. Now let's square both sides of this equation. So when we square a square root, we're going to square a square root, and that's we square this side, parentheses around it, square that side. But when we square a square root, that's equal to just 1. So okay, let's square both sides. Well, we square this side, and with the left side, we get y squared. And we square the right side, we get 4a squared minus 4a times the square root of this quantity inside of here, plus the square of minus c minus x squared plus y. This minus c plus x minus c minus x squared plus y is this term in here. So that's 2 times 2a times 2a is 4a squared. 2a times the square root of this times 2 is 4a squared. And the square root of this quantity times itself leaves this quantity right there, if you remember your algebra. So therefore, we'll take the c minus x and square it. The c minus x and square it, and this is what we get. C squared minus 2cx plus x squared. And we take the minus c minus x squared and we square it. And we get c squared plus 2cx plus x squared. And what we do is we take this minus c minus x squared and move it to the left side. If we change the sign on it, we leave the 4a squared minus 4a times the quantity square root quantity on the right side. Okay, let's continue. Here's our previous equation. And so now what we do is we add these together. And we distribute the minus sign. And lo and behold, we see that minus c squared plus c squared plus c squared minus c squared cancels. We see plus x squared minus x squared cancels. And that leaves us with minus 2cx minus 2cx. Okay? And then we add those together. And this is a lot of algebra. Okay? And now what we do is we divide through by 4. Okay? And I'm dividing through by 4. Divide through by 4. And that leaves us with minus cx is equal to a squared minus a times the square root of this quantity. Okay, so what I'm going to do is I'm going to take this minus a times the square root and move it to the left, and take the minus cx and move it to the right, and make that positive. Okay. Now square both sides again, and we square both sides again. And we get a times a squared times the square of this square root is just 1. So that's what we leave here. A squared, and the square of this quantity is just what's inside. Okay. And we square both sides, and that's a to the fourth plus 2a squared cx plus c squared x squared. And then we square what's on the inside, and then we multiply through by x squared. And lo and behold, we get something else that cancels. 2cxa squared cancels on both sides. Now, rearranging terms, we get a to the fourth, a squared, c squared, we move that to the right, and we move, that leaves us a squared x squared plus a squared y squared. And we move c squared x squared to the left. We're just rearranging terms. And then we factor out x from this minus c squared x squared and a squared x squared. So that leaves x squared times a squared minus c squared plus a squared y squared equals a squared times a squared minus c squared. We just factored out an a squared. If we multiply through again by a squared, you get a squared times a squared is a to the fourth. A squared times minus c squared is a squared times c squared. So we just factored out. Okay, let's continue. Here's our previous equation. Dividing through by the right side of the equation. So we're going to take this whole right side of this equation and divide each term right here. Well, the top divided by the top is equal to 1, okay? And so on the left-hand side, the a squared minus c squared is canceled. And on the right side, with the y's, the a's cancel. And that leaves x squared over a squared plus y squared over a squared minus c squared is equal to 1. Let's continue. Okay, here's our ellipse. And what I've done is I've taken point D and I've moved it to the top of the ellipse. And in so doing that, we have a right triangle. From the center of the ellipse to the top is our semi-minor axis B. From the center of the ellipse to the first foci, we have our distance C. And from the foci to the top of the ellipse is the semi-major axis A. So from the Pythagorean theorem, we have a squared is equal to b squared plus c squared, where the eccentricity is equal to c divided by a. So here's our previous equation, where a squared equals b squared plus c squared, and the eccentricity is equal to c divided by a. From our Pythagorean theorem, a squared equals b squared plus c squared. If we move c to the other side, then we have b squared is equal to a squared minus c squared. Well, here in our equation, a squared minus c squared, so therefore that's equal to b squared. So therefore the equation of the ellipse is x squared divided by a squared plus y squared divided by b squared is equal to 1. If a and b is equal to r, then x squared over r squared plus y squared over r squared equals to 1. And if we multiply both sides by r squared, we have a circle. Let's continue. And that's it. Everything you need to know, derive the equation of the ellipse. That was great. That was fun. So in part 2 of the next video, we will derive the area of the ellipse. That was fun. I enjoyed doing that. It's not magic, it's the law. Until next time, thank you.